Dear friends, a very good morning to all of you and welcome to the second session on manipulator kinematics. Before going to this session, let me have a brief recap of what we discussed in the last class. So in last class we started with defining the coordinate system. How do you define a coordinate system? Basically discussed how do you define a point in space and how many degrees of freedom we need to have in order to manipulate objects. And then we talked about coordinate transformation. How do we transfer one coordinate system to another coordinate system? Basically the transformation matrices we discussed. And then we talked about the fundamental rotation matrices and fundamental translation matrices. And then the homogeneous transformation matrix, which is basically a 4x4 matrix, which represents the transformation from one coordinate system to another coordinate system, which may include both translation and rotation of coordinate frame. And we briefly discussed about the manipulator joints, the type of joints normally used, and then how the classification of robots can be done based on the joints like RRP joint robot or RPP. Like that, we discussed the different configurations also. After that, we looked at the two important issues about the parameters. We discussed about the joint parameters and link parameters, which actually also known as Denavich and Hartenberg parameters, which describe the configuration of a manipulator. For each joint, we can actually identify for a pair of joint and link, we can identify two joint parameters and two link parameters. And out of these two joint parameters, one joint parameter is a constant and the other one will be a variable. And the two link parameters are always a constant for a given manipulator. That was what we discussed in the last class. And we found that this joint parameters, joint angle and joint distance, and the link parameters, link length and link twist angle completely define the configuration. And if you have a n degree of freedom manipulator, we will get foreign link joint and link parameters or the kinematic parameters, which can be used for describing the or developing the forward kinematic relationship. That was what we discussed in the last class. So today we will take this forward. We talk about formulating the forward kinematics for a manipulator. So as you know, we need to manipulate objects in space, and in order to manipulate objects in space, we need to look at the position and orientation of the robots, and that is to be specified in a three-dimensional space. So if you have a manipulator which is given like this with a base, and you have the joints and the links. So you can have different kinds of joints and an end effector. So we call this the manipulator in three-dimensional space. If you have the coordinate frame, so we can actually specify the position and orientation of this tooltip in the three-dimensional space or a Cartesian space with the x, y, z and the theta, phi and psi, the vector or the pose parameters, position and orientation. This is basically known as the Cartesian space coordinates of the robot. So the Cartesian space robot, the position will be and the vector will be in terms of x, y, z and the roll, pitch and yaw angles, or we can actually have the normal sliding and approach vector also for the orientation parts. And this can be achieved by changing the joint parameters, which are the variables. So if you have joint parameters which can actually be varied, basically the theta 1, theta 2, etc. up to theta n, and these are known as the joint parameters. So these joint variables or the joint variables, these are the joint variables. So a relationship between these joint variables and the Cartesian space of the robot need to be developed. So a relationship between the joint variables and the position and orientation of the tool is to be formulated in forward kinematics, and that is what we are trying to do. We try to map the joint parameters. So we need to make the joint variables, not joint parameters, joint variables to the Cartesian space is to be formulated, and that is what we call as the forward kinematic relationship. That is, whenever I change the joint variables theta, what will be the change in the position and orientation of the manipulator need to be identified, and that is known as the forward kinematics or direct kinematics problem. Given the vector of joint variables of a robotic manipulator, determine the position and orientation of the tooltip with respect to the base frame is known as the direct kinematics problem. That means you know these variables, and if I know these variables, how do you find out the position and orientation of the tooltip? Or effectively, you can actually say that this is a this is the position, and this position vector need to be obtained with respect to this base frame. So what is this position of this tooltip with respect to the base frame need to be identified, as well as you need to know what is the orientation of this one with respect to the base also need to know what is the angle of this x with this x, what is the orientation of y, this coordinate frame to this coordinate frame also need to be obtained. So position and orientation of the tooltip with respect to the base frame, if the joint angles are given to you, how do you find out? That is basically the forward kinematics problem. So to do this, we need to have a proper formulation. We need to identify, or we need to see in what way, or in a systematic way, how this relationship can be developed for a given manipulator is the direct kinematics problem. So let us see how this can actually be developed. So to do that, we start with the basic problem of assignment of coordinate frames first, and then we go with the formulation of relationship between joint variables and Cartesian space. So the first point, or the first starting point, is basically assignment of coordinate frame. So when before to do this, let me warn you that there are multiple ways to do this, or there are textbooks which actually do it in different ways. So if you look at the book by John Craig, it will be done in one method, and if you look at Schilling, this will be done in a different way. Though both of these methods will lead to the final result, the same result, the way it is the approach to the problem and assigned coordinate frames are slightly different, and therefore you need to follow any one of the methods. So whichever is easy for you, you need to follow. I normally follow this method, Schilling method, which is available in the textbook by Schilling, which actually starts with a base coordinate frame of x0, y0, z0. But in Craig there will be a frame, the first joint will be always x1, y1, z1. So that is the some basic differences will be there, and therefore you can follow one of the methods, and both the methods will lead you to the same answer. So not need to worry which one you follow, but as long as you follow one of these methods and do it properly, that will be good. So we'll go with the basic method of Denavage and Hartenberg for identifying that assigning the coordinate frame, and then getting the DH parameters for each all the joints, and then getting the formulation for coordinate transformation. So let us start with a simple robot system, and what we do first is, what we do is a systematic notation for assigning right-handed coordinate frame to all the joints, and this transformation between adjacent frames can always be obtained by using the transformation matrix. So what we are trying to do is we have assume that there is a robot, as I shown you in the first case. So we will have a robot manipulator like this. So the first step is basically number the joints and links. So we start with numbering the joints and links. So we always start with link 0 as the base. So I put it as a 0 as the base, and then link 1, link 2, link 3, etc. till the last link. So depending on the number of degrees of freedom, you will be having n links attached, and then the joints will be numbered. The first joint is a rotary joint, so we number it as J1, and then this will be J2, J3, J4, etc. till the last joint. So the joint 1, 2, 3, etc. will be assigned first. So we will have number the joints and links of the given manipulator. Then so number the joint from 1 to n, and the links also. The numbering of this last 3 joints will be 4, 5, 6. Normally in the 6 degrees of freedom manipulator, you will be having first 3 joints for positioning and the last 3 for orientation. So that will be like roll, yaw, pitch, roll. So that is in the order you will be doing yaw, pitch, and roll. So the roll axis will be the last one. So the roll axis, which is actually the rotation with respect to this axis, will be the last one, and yaw, pitch and roll. So basically with respect to X, Y and Z, the rotations we normally call it as yaw, pitch, roll. So this will be the order in which you will be assigning the last three joints, and the first three will be for positioning, last three for orientation, yaw, pitch, roll. And once we do this, we start with the first coordinate frame, which is the 0th frame. So that is the first coordinate frame will be assigned as a right-handed orthonormal coordinate frame. So we call it as L0. The coordinate frame is defined as L0. The first coordinate frame is L0, and then we will be having L1, L2, L3 as the coordinate frame. And for this one, the point is that always the joint axis will be assigned as the Z axis. So Z axis will be always the joint axis or the rotation axis of that particular joint. Here we know that this is in the vertical axis and it is rotating this way. So we will always assign a Z axis here. So we call it as the Z0 axis. And now we assign a right-handed coordinate frame at this point. At the base joint, we assign a right-handed coordinate frame. A right-handed coordinate frame is like your right hand. So take this this as the right-handed coordinate frame. So the thumb represents your x-axis, and the middle finger represents the z-axis, and the pointing finger represents your y-axis. So this is the way how you assign the right-handed coordinate frame. So if I put it like this, so this is my x-axis, this is my z-axis, and that is going inside is the y-axis. So I'll put this as x-axis, x0, and this as y0 axis. So you can look at this. So this is a coordinate, orthonormal coordinates. All the axes are orthogonal. So you can see that this is the green is the x-axis, red is the z-axis, and blue is the y-axis. So I'll actually put it like this. So you can see this is the x-axis, z-axis, and y-axis. So this is the coordinate right-handed coordinate system. You always follow the right-handed coordinate system for all these. It can be have any rotation. You can actually have it in rotated. You can have whatever maybe the axis you want, and you will be able to find out the coordinate corresponding to that. So this is the x0, y0, z0 axis. Okay, so this is the, but it's actually projecting inside the plane. That is x0, y0, z0. So this is the first coordinate frame we assign to the joint. So the z-axis always aligns with the joint axis, and then x0 we normally take it to the positive direction of the manipulator. So the manipulator is assigned in this direction. So naturally we assign it as x in the positive direction, this direction. You can always have the rotation also, but for convenience we take this as the positive direction of the manipulator. So this will be the x-axis. Now we go to the next joint. So we need to assign coordinate frame to all the joints. So the next one is taken basically like k is equal to 1. We start with k is equal to 1. That is the next one. And for this axis, zk, align zk with the joint k plus 1. So you have this joint 2 and align the axis of z with this joint axis. Align z with the joint axis. We know that this is actually rotating with respect to this axis, and therefore the z will be like in this direction, that is actually projecting into the board. So it is actually rotating with respect to this axis, and it is moving up and down, and therefore we will be able to see that this is the axis. So if you look at this, will be something like this. So this is the joint. So you can see this is the joint which actually moves, and this is the axis. So this axis is actually projecting into the board. So we will take this as the joint axis here. So this is the joint axis. The joint axis can be like this. It can be like this. So this is the Z1 axis. Now the next point is important. We need to identify the origin of this coordinate frame, because the first origin was actually at the first joint, and further the joint, the physical joint and the coordinate origin need not be the same. They can be different, and therefore we need to find out what is the origin of this coordinate frame L1. So the coordinate frame is L1. We need to find out the origin of this coordinate frame, and that is obtained by looking at the intersection of zk and zk minus 1. So look at the intersection of zk and zk minus 1 and take that as the origin of this coordinate frame. Now you can see that this is Z0 and this is Z1. So it actually intersects at this point. So we take it as L1. So as I told you, it need not be always at this joint. It can be somewhere else also. But how we have to look at this is find out whether they are intersecting or not. If they are intersecting, take the intersecting point. And if they are parallel, if suppose these Z1 and Z0 are parallel, then we need to take a common normal between these, and then the intersection of the common normal with ZK to be identified as the origin of the coordinate frame. So that is the origin of the coordinate frame, and then you take the Z axis along the positive direction of this again. So this is the Z axis, and then you identify the X axis, which actually points away from Z0 and Z1, or basically normal to both these axes, Z0 and Z1, because Z0 is in this direction, Z1 is in this direction, and therefore we need to identify a normal to these two. So Z0 is vertical direction, Z1 is this direction, and therefore X should be in this direction, because Z0 is in this direction and Z1 is in this direction, Z0 and Z1, and therefore X should be normal to these two, and therefore the joint axis will be along this one. So basically if it is straight, it will be along the axis, so it will be the X1 axis. And once you get X1 and Z1, you identify the Y axis using the orthogonal this right-handed coordinate frame. So it will be, this will be the axis. So this is the X axis, this is the Z axis, the red one is the Z axis, and this will be the Y axis. So the Y will be like this. So Y1 will be like this. So you have X1, Z1 and Y1, both are the three axis identified. That this is the coordinate frame assigned to the second joint. So that is the second step, identifying the coordinate frame. So you look at the axis, Z axis, then locate the origin Z1, origin of LK at the intersection of Z1 and Z0, and then if they do not intersect, take the normal, otherwise you take the intersection, and common normal take, if they are not intersecting, take the common normal, and then select xk to be orthogonal to both Z1 and Z0. So take xk to be orthogonal to Z1 and Z0. As I told you, Z1 is in this direction and Z0 is in this vertical direction, and therefore X will be orthogonal to both of these. So you will be getting X, Y and Z axis for this origin. So that is the way how you do this. Now we have to continue this for all the joints, because we need to apply the same algorithm, like for this one, for this joint, again we know this Z1 axis, this also rotates in the same axis. So Z1 and Z2 will be parallel. This is the Z2 axis, because it will be like this and it passes through this, and we need to find out the intersection of Z1 and Z2 to get the origin L1. So L2, we don't know where is L2, the origin of the coordinate frame. So what we do is, we look at Z1 and Z2. If they are intersecting, the intersection point will be the origin. If they are not intersecting, take a common normal between these two. So the common normal will be like this, and the intersection of the common normal with Z2 will be taken as L2. So that will be the origin L2, and the same way you will be getting X and Y, because the same thing. So it will be X3 and Y3. That is the way how the coordinate frame will be assigned for the second one, and it will continue with this. It will be more clear when we do take an example and then try to assign it, but I am just explaining you the principle of assigning the coordinate frame. We will continue with this till we assign the last frame, k is equal to n. We need to go till k is equal to again by right-handed coordinate frame, and then k is equal to k plus 1. We continue this, and till k is less than n. So till k is less than n, we will continue this, and when k is equal to n, we actually assign the last coordinate frame at the tooltip. Okay, so the last coordinate frame, the origin of Ln, the last one will be at the tooltip. So we will put this as the Ln. So if you have 5 degrees of freedom, this will be L5. If you have 6 degrees of freedom, this will be L6. And assign the coordinate frame like that. This is the approach vector, that is the along the roll axis of this tip, the last joint. You assign the Zn, that is the last Z axis, and the open close direction you give the Y, and then the normal to this. Normal to this will be the X axis. So that is the approach, sliding and normal vector. Normal will be projecting to the board. So that will be the again a right-handed coordinate frame will be assigned. Zn, Yn and Xn will be the last coordinate frame. So if you have n degrees of freedom, we start with x0, y0, z0, and then n with xn, yn, zn. That is the way how you assign the coordinate frames to the manipulator. Okay, so that is the first step in identifying the or assigning the coordinate, right-handed coordinate frame to all the joints. Okay, fine. So let us go to the next part of the algorithm. So the first step is basically to assign the coordinate frame, assign the right-handed coordinate frame to the joint. Now we need to identify another imaginary point bk. We need to identify a point bk. This is basically to get the DH parameters at a later stage. So we'll identify a point bk as the intersection of xk and zk minus 1. So we want to identify a point bk. So bk is an intersection of xk and zk minus 1. Xk and z minus 1. So b1 will be, the point b1 will be intersection of x1 and z0. Similarly, x2 and z1, x3 and z2 will be identified. So b1, b2, b3, etc. will be identifying. So now look at this assignment of coordinate frame. So you have the b1, point b1 can be identified as an intersection of x1 to z0. So you can see x1 to z0. So this is x1, this is the x1 axis, and z0 is this, the vertical axis. They actually intersect at this point, and this will be marked as b1. So we will be marking it as b1 here. So this will be the b1 point. And similarly, b2 is an intersection of x2 and z1. Now you look at b2, x2 and z1. So this is x2, this is x2, and this is actually intersecting with z1 at this point again. So x2 will be assigned in this direction, it will be intersecting at this point, and this will be b2. So b1 and b2 will be at the same point in this because of the intersection of x2 at here and z0 and x1 here. Therefore, b1 and b2 will be at the same point. Another important point when we assign x axis is that it should always point towards the previous joint. So x2 should always intersect with the previous joint is one consideration for assigning the x axis also. And similarly, you can identify b3 will be here and b4 will be here and b5, okay, depending on number of joints. So bn will be at the tooltip, you will be able to see. So identify all the points bk. So I'll get bk as the points with the intersection of xk to xzk minus 1. So bk will be an intersection of xk axis and zk minus 1 axis. That's what we do in the next step. So we'll get the b1 here, and then we'll get a b2 also, as you can see in the slides. You'll be getting b1, b2, etc. I think okay, it's not shown in the slide, but b1, b2, b3, etc. you will be able to get. And you k is equal to k plus 1, you will be getting all these. Okay, compute theta k. So the next step is theta k. So you need to identify the joint parameters theta k, dk, and ak and alpha k for this joint. So that is the next step in the algorithm. We need to compute theta k. So theta k is the joint angle. So theta k is the angle between xk minus 1 to xk. So theta k is angle xk minus 1 to xk measured along zk minus 1. Okay, so it is measured about zk minus 1. So you measure the rotation of x0 to x1, along zk minus, about zk minus 1. So about z0, how much x0 has moved between these two. So zk minus 1, about z0, how much is x0 to x1 movement. Similarly, theta 1 will be x0 to x1 and theta 2 will be x1 to x2. So what is the angle between x1 and x2 will be theta 2, that again with respect to this axis, Z1 axis. Similarly, x2 to x3, what is the joint angle? That will be theta k. So theta k can be considered measured with respect to zk minus 1, and what is the angle between x0 and x1 will be k minus 1 to xk will be the joint angle theta k. And then dk is the distance from the origin of frame L k minus 1. So this is L k minus 1 to the L k minus 1 to bk. So dk is measured as the distance from origin Lk minus 1 to point bk measured along zk minus 1. So measured along zk minus 1. So along zk minus 1, what is the distance from L0 to b1? So d1 will be, so d1 is L0 to b1 measured along z0. You can see here, this is L0, the origin is L0 and b1 is here, and along z0 you have a distance of this distance. So this will be the d1. So d1 will be this distance, L0 to b1, and then next one will be L1 to b2, L2 to b3, like that. You will be getting d as the joint distance. In some cases it will be a variable, in some cases it will be a constant. And then AK is the link length. So AK is the distance from point BK to the origin of LK. So this is BK to LK, BK to LK measured along XK. So the distance from point BK to the origin of frame LK, so BK to LK measured along XK. So that is basically AK. So A1 will be B1 to L1 along X1. So this can see B1 to L1 both are at the same point. So this will be 0 in this case, A1 will be 0. In some case B1 to B2 to L2. So B2 to L2 will be A2. So you can see this is B2 and this is L2. So B2 to L2 will be A2. So A1 will be 0 in this case, A2 will be having some value. So that is basically the link length AK. And alpha K is the angle between two successive joint axes. So alpha K is the angle of rotation from Zk minus 1 to Zk, Zk minus 1 to Zk measured about Xk. So this is measured about Xk. So about Xk, how much is the rotation from Zk minus 1 to Zk? So you can see here, this angle is like this, this z-axis. So you can see this z-axis is like this z-axis is like this, and this z-axis is like this. So there is a rotation of 90 degree for this to become like this. So this joint axis has changed by this much. So that is the alpha, and you measure about this x-axis. So this is the x-axis here. So now this is the x-axis for this joint. So how much it has rotated to become this position. So it was initially like this, this one, this was like this, and now it has rotated by this 90. So by clockwise it has changed 90 degree. So this clockwise rotation of 90 degree is the alpha K here. So like this we need to look at each joint and then identify what is the alpha for each one. So alpha 1 will be 90 degree and counterclockwise. So clockwise is always taken as minus 90, counterclockwise will be taken as positive. So clockwise is minus, counterclockwise is plus. That is the convention used for calculating the twist angle. So twist angle is always Z0 to Z1 or Zk minus 1 to Zk measured about Xk is the twist angle. So by assigning these coordinate frames, so we will be able to assign the coordinate frame first and then look at the joint, then assign the this point Bk, and then using this Bk and origin L0, Lk and the other joint axis, we will be able to identify all the joint parameters for the joint and link parameters for the manipulator. So if you have n joints, you will be able to identify for n parameters, DH parameters corresponding to the given manipulator. So that is the DH algorithm which helps us to identify or which helps us to assign coordinate frame and then get the all the kinematic parameters necessary for defining the complete kinematics of the. Okay, so two important notes about assignment of coordinate frame. Always x-axis should be, xk should always intersect with the z-axis, zk minus 1. As you can see here in the slide, you assign the x-axis, that the red line shown here, in such a way that it actually intersects with the previous joint axis. That is the way how we assign the xk. And another point is that it is not a unique algorithm, because we can always have the z-axis in a reverse direction. So I always assume the z-axis is in this direction for a rotation with respect to vertical with respect to this axis. You can always think of assigning it in this direction also, and therefore you will be getting a different y and x direction because of the right-handed coordinate frame. So it need not be always unique, but finally the parameters you will get unique parameters which actually corresponds to that particular configuration of the manipulator. So just to make it clear, let us take an example and then see whether we are able to or you are able to assign the coordinate frames. So as I explained, you try to do it yourself and then check whether you are actually doing it right. So look at this robot as shown in the slide. It's a commercial robot Alpha 2, just a 5-axis robot. So it's a 5-axis robot. So it has got 3 positioning axis and 2 orientation axis. It has got a tool pitch and a tool roll. There is no tool yaw in this case. So it's a 5-axis robot. We need to assign or we need to find out the forward kinematics of this manipulator. So let us start with assigning the coordinate frame, right-hand coordinate frame, and then getting the DH parameters. So to make things easy, what we always do is to assign or identify a home position. A home position is that since the joint angles are variable, so you can see here the shoulder joint, base joint, elbow joint, all these are variable. We can always assume a particular position and start with the assignment from that position. So it's always good to start with a home position. So I will say the home position is like this. This is the first vertical joint here. This is the vertical joint, and then you have a shoulder, and I assume that the shoulder joint is actually pointing this to this direction. So this is the way, and then you have another joint and another joint and the last joint as the tool tip. Yeah, a roll axis here. So this is one joint, this another joint, a joint here, and this one. So this can be considered as the home position. You can even use a line sketch like this. You can say so. I start with a simple home position for easy analysis. So that will actually help you to analyze it easy. Since it's a variable, it can take any position. It can be vertical, it can be like this, it can be vertical at this point. All these are joint variables. So any position we can take as the home position. And then as usual, we assign the link 0, 1, 2, 3, 4, and the last one. Last one will be the tool end will be the 5th one. So we will assign like this. 4th and 5th is the tool or the last one. It will be the 5th one. And the joints are, this is joint 1 and joint 2, joint 3, joint 4, and joint 5 will be here because it's a roll axis. It will be along this, we will be having another joint. So joint 5 will be the 5 joints. So that is the first step. You assign the numbers, joint numbers and link numbers, and start with the base coordinate frame. So the base coordinate frame, as I told you, the z axis will be always this direction, the joint axis, and x will be assigned the positive x direction. So it will be x0, z0, and then a right-handed coordinate frame. So now you can assign a right-handed coordinate frame at this point. X0, Y0 here shown. Find out what will be the y direction. What will be the y direction? So you can see this. So this is the Z axis, X axis, you have Z and X, and therefore you can see Y will be projecting inside to the board, so it will be Y0. That is the L0 frame, or the L0 origin of the first coordinate frame. So as you can see here, this is Z0, X0 and Y0. Now the next step is to get the second coordinate frame, or origin of the coordinate frame and the origin of the frame. So what we do, normally what we have to do is to align the Z axis with the joint axis. So the joint axis is like this, vertical and perpendicular to the boards. So I'll assume it as this direction. This is Z1, and I don't know the origin, so I'll just make it as Z1 in this direction and try to find out where is the origin. So how do you get the origin? The origin is actually obtained by intersection of Z1 and Z0, or Z0 intersect with Z1 will be the origin. So you can see that it actually intersects here, and therefore this will be L1. The origin will be L1 will be at this point. And next one is X1. X1 should be always normal to Z1 and Z0. So X1 is normal to Z1 and Z0. So Z0 is this direction and Z1 is in this direction. Okay, so Z0 is this direction, Z1 is in the pointing to the boards, and therefore X should be in this direction, because it should be always normal and orthogonal to these two. So it will be in this direction. So Z will be taken in this direction. That will be X1. So now we look at the frame. So you have a Z axis here and you have an X axis here, and therefore you need to find out the Y axis. Y axis it should form the right-handed coordinate frame. So this is the right-handed coordinate frame. So look at the Z axis. Red is the Z axis. Z axis is pointing inside. X axis is in this direction. Therefore the Y will be in this direction. So you have Z1, X1 and Y1 axis like this, the right-handed coordinate frame. I hope you are following. Again, if you have any confusion, please stop me, raise your hand, and we'll try to explain it. Okay, so we'll continue this. The next one will be J3. You can see J3 as a joint 3. 1, 2, 3. Again, the axis will be like this. J3, because it's again the same rotational axis. And we need to identify the origin. So this will be Z2 is the axis. Origin will be the intersection of Z2 and Z1. So that is basically how it is defined. The origin will be the intersection of Z2 with Z1 with Z2. And unfortunately they are not intersecting. You can see that Z1 and Z2 are parallel. So if they are parallel, what we need to do is to take a common normal between two and see where it actually intersects with the Z2. So this is the common normal between Z1 and Z2, and it intersects at this point, and therefore L2 will be here only. So we'll get the origin L2 at this point, and again Z1 and Z2 should be always these are the direction, and X2 should be always normal to these two. That is the condition. X2 should be always normal to this condition, these two, Z1 and Z2, and the other condition is that X2 should intersect with the joint 2 also, like the condition I mentioned. So X2 should actually intersect with this one, therefore X2 should be in this direction, because if I take X2 in this direction, it will not intersect here, and therefore I need to take X2 in this direction. So I have X2, L2, and similar to this you will be getting Y2 in this direction here. So you have X2, Z2 and Y2 here. This is L2. So again we go to the next one. So J4 also is at the same axis, rotational axis, and therefore we put it as Z3. So you can see that 3 joints are having parallel rotation joints. So rotational axis, these 3 are having same rotational axis, parallel to each other. So this will be Z3, and again it will follow the same rule. So you have the ZX3 and Y3. Okay, up to this it is fine. So Z1, Z2, Z3 these are parallel, and the common normal you will find out. The origin will be here. So L3 will be at the origin of this point because it intersects. Z3 and Z2 won't intersect, but the common normal intersect with Z3 at this point. So L3 will be at this point. So L3 will be here, L2 will be here, L1 will be here, and L0 is here. Now is the slightly interesting problem coming up. Now look at the next joint. The next joint is a roll axis. Okay, so it's actually a roll joint. So this roll joint has got an axis like this. Okay, this is the Z axis. So Z4 is like this because it's a roll axis. So Z4 is the axis like this. We need to find out the origin of Z4, this coordinate frame. So where is the origin of this coordinate frame? Now if you look at the rule, the origin will be actually at the intersection of Zk minus 1 and Zk. That means L4 should be at the intersection of Z4 and Z3. Now you can see that the roll motor will be somewhere here which actually rotates this one, but the origin of the coordinate frame will be always at the same point because Z4 is this way, Z3 is this one, so it actually intersects at this point. There is no other intersecting point, and therefore L3 and L4 will be at the same point. The origin of the coordinate frame L3 and L4 will be at the same point because Z4 and Z3 intersect at this point, and therefore the origin will be at the same point. For clarity, I just mark it somewhere here. Okay, just a dotted line, and just for clarity, I just show that it is here. And this is Z4. Okay, so Z4 and Z3. Now we have to find out at X4. X4 will be normal to these two. So one is Z3 is like this, Z3 is like this, and Z4 is like this. So X4 should be like this because it should be normal. Z3 is in this direction and Z4 is in this direction. So X3, X4 should be in this direction. And then we assign the right-handed coordinate frame. So look at this. Okay, this is Z, X, and Y should be like, okay, projecting out. Y4. So you get X4, Y4 and Z4 here, and this is going to be the L4. It is at the same point. Okay, L3 and L4 at the same point. So K is less than N, we have completed. Now K is equal to N. So K is equal to N, that is 5. We find out the last coordinate frame at this point. So this will be the L5. The tooltip will be L5. That is the origin of the coordinate frame. And then this will be the Z axis because we already mentioned that the Z axis should be always aligned with the roll of the tool. And then this will be the Y5, and then you get the X5 as the normal. So it is Z5. So this is Z5 and this is X5, sorry, Y5, and this will be the X. So X will be like this, X5 will be like this, projecting out of the board. So now we got all the frames, L0 this way, L1, X1, Y1, Z1 here, and L2, X2, Y2, Z2, L3, X3, Y3, Z3, and L3 and L4 at the same point, origin, and Z4, X4, Y4, and the last one at the tooltip, L5, Z axis, Y axis in the open close, and Z axis normal to these two. So you have X, Y, X, Y, Z of fifth frame also obtained. So 5 frames, a 5 axis joint, you have up to XY, Y5, Z5, starting from L0, X0, Y0, Z0. So this is the way how we assign coordinate frame to a manipulator. So once we know the configuration, given manipulator configuration, we look at, we identify a home position, any position you can assign, and then try to assign the coordinate frame based on the DH algorithm, which starts with an L0 and goes on till L5, assigning a coordinate frame at the tooltip. So this is the way how the Schilling method works for getting the coordinate frames for the robots. Okay, so it's here. So you can see that first joint axis, then second one, third one, and the fourth one, and the fifth one at the same point. So we just marked it as a dotted line, Z4, X4, Y4, and then the last one, XY, Y5, Z5. So this is the last one, Z5, and So this is the way how we get all the coordinate frames and the origin of coordinate frame. The next part then the algorithm is to identify the points BK. So we need to get the point BK. So BK is defined as the intersection of L0 to x1 like that. So Lk to k minus 1. So we'll get it as locate BK intersection of xk and zk minus 1. So BK is intersection of xk and zk minus 1. So B1 will be x1 to z0. So you know x1 is this one and z0 is this one. So intersection of x1 and z0 is this one. So B1 will be here. At this joint will be the B1. And then we'll be looking at the next one. So B1 is here. B1. And the next B2 is x2 and z1. So what is the intersection of x2 and z1? So x2 is this one, x2 is this axis and z1 is this. The intersection of x2 and z1 will be here. So again it will be B2. So this is B2, B1 and B2. Now B3 will be x3 to z2. x3 to z2 will be B3. So look at B3. B3 will be x3. So this is x3 and this is z2. So the intersection will be here. So we will be having B3 here. And B4 is x4 to z3. So this is x4 here and z3 is here. So both are at the same point. So we will be having B4 here. Because this x4, this origin is at the same point. So x4 is this point and z3 is also here. You will be having B4. Next one is B5, x5 and z4. So x5 is here vertical and z4 is here. So the point will be at here. So B5 will be here. At the last point will be B5. So you have B1, B2 at the same point, B3 here, B4 here and B5 at this point. B5 is basically x5 to z4. So x5 is a normal here. So it is at this axis and z4 is in this direction. This is z4. From here it is in this direction. It actually intersect at this point and that will be the B5. So you have all the BKs identified. There is no B here. So B1, B2, B3, B4 and B5. That is the next step in algorithm. So I identified all the BKs here. So once you have these BKs, next task is basically to look at the parameters, the DH parameters. How do you get the DH parameters from this assignment? So theta k is basically xk minus 1 to xk. So it's a variable. So what we do, we'll actually make a chart. So you have link 1, 2, 3, 4 and 5. I mean joint 1, 2, 3, 4, 5 and we need to identify all the parameters for this. You have to find out theta, d, a and alpha. Okay. So this will be theta, d, a and alpha. For each one you need to identify these parameters. Because this is the 5 degree of freedom manipulator and therefore you will be having 5 into 4, 20 parameters and theta is the joint parameter which is a variable which actually is measured with like xk minus 1 to xk. So what is the angle between x0 and x1 with respect to z0? How much it has to be rotated to get x0? And since it's a variable, it will be for this position you will get some magnitudes, but for this can actually change depending on this joints. It will be changing. So for the time being, we are not interested in actually knowing the exact values. So what we do is we just make it as theta 1, theta 2, theta 3, theta 4 and theta 5 as variable. Yes, we are not really interested in knowing the actual values for the time being, because again it's a variable. Depending on the position of the manipulator, it will keep changing. So we just look at this as a variable and then we look at what are the other things which are not variable. We'll identify the fixed parameters. So the fixed parameters, next one is dk. Dk is the joint distance and it is mentioned as Lk minus 1 to Bk measured along Zk minus 1. So we need to find out the distance from Lk minus 1 to Bk along Zk minus 1. So now look at D1. So D1 will be L0 to B1. So the distance from L0 to B1, K minus 1 to Bk, L0 to B1 along Z0. So what is the distance to be travelled from L0 to B1 along this axis? That is basically the D0 or D1. So this is basically the D1 parameter. And if you look at the manipulator, you will see that D1 is 215. So numerical value of this one is given as 215. So this will be 215. D1 is 215 for the given manipulator. And then we look at D2. So D2 is nothing but L1 to B2. Now we know that L1 is here and B2 is here. Both are at the same point. So this will be 0. Similarly, L2 to B3. B3 is here, L2 is here. So it will be 0. Then L3 to B4. This is L3 and this is B4. L3 to B4 is 0. And then last one D5. So D5 is L4 to B5. So that is D5. So D5 is L4 to B5. You can see that L4 is here at the same point, B5 is here. So this distance is D5. So this is D5, and this D5 will be obtaining from the diagram as 129.5. So you can see that from the diagram it is 129.5. So we got all the joint distance parameters. It is 215 for D1, D2, D3, D4 0, and D5 is 129.5. This distance is 129.5. That is D. Now look at the AK, that is the link distance AK. So this is theta over. So now look at link length AK. Link length AK is B1 to L1. So B1 to L1 is A1. So A1 is equal to B1 to L1. The distance B1 to L1 along X1 is A1. Now look at B1 to L1. So this is L0, this is L1, that is the origin L1. This is L1, this is B1. So L1 to B1 is 0. Therefore A1 is 0. Then B2 to L2. B2 to L2 is the link length. So this is B2, this is L2. So this distance is A2. You will get this as A2, and A2 as per the diagram is 177.8. And then this one, next one is, this will be the A3, you will get this as A3, because A3 is B3 to L3. So this is B3 and this is L3. So B3 to L3 is 177.8, and similarly this will be again 177.8. Again this will be 177.8. Next one A4 is B4 to L4. You can see this is B4 and L4 is also at the same point. The origin of the coordinate frame is at the same point. So B4 to L4 is 0. There is no distance. And A5 is B5 to L5. So B5 in L5 are at the same point. So A5 is again 0. So the link length A2 and A3 has got some value, and others all will be 0. The last one is alpha. Alpha K. So alpha 1 is the angle between Z0 to Z1 measured about X1. So Z0 to Z1 measured about X1. So I told you, you can look at this Z0. So this is Z0. So this is the Z0 and this is the Z1. So it is like this. This axis is like this. Z1 is like this, and this is the X like this. X1, Z1, and Y1. Now this is X1. So with respect to this axis, I have to measure what is the angle between this one and this one, or how much this has rotated to this one. So initially it was Z0 was like this vertical this way, and it has rotated to go like this. So from this position of Z0, it has moved like this to Z1. So Z0 has rotated 90 degree with respect to this to come to this position like this, and therefore it has moved from this position to this position. So it has moved from this position to this position in a clockwise direction, and therefore this 90 degree, it's rotated 90 degree and the angle is minus, so it will be minus 90 will be the alpha in this case. And then alpha 2, the same way alpha 2 will be Z1 to Z2 about x2. Okay, Z1 to Z2, so Z0 to Z1 there is an angle, Z1 to Z2, is there any angle? Because they are parallel, there is no rotation, so alpha will be 0. In the next case also Z2 to Z3 also it will be 0. So there is no angle between Z1 and Z2, Z2 and Z3, therefore these two will be alpha 2 and alpha 3 will be 0. Next one is Z3 to Z4, so Z3 is actually like this, Z3 is projecting into the boards and Z4 is actually like this. So it actually come from this position, it has actually moved to this position and Z4 is actually vertical. So we have to look at from the vertical angle, so how much it has rotated. So from this, looking from this point, so this position now, this is the position now x4, z4 and y4, and initially the z4 axis was like this, it was like this, it has rotated this direction from inside pointing towards the board, the initial z3 it is rotated like this. So if you are looking from here, it has actually moved 90 degree clockwise. So if you are looking from here, it has moved 90 degree clockwise and therefore again this is minus 90 degree Z4. And then next one is Z4 to Z5, they are actually parallel, that there is no angle, so this will be 0. So by assigning coordinate frame and then looking at the B1, BK and LK, we are able to identify all the kinematic parameters or the DH parameters of the manipulator by these methods. So that actually the DH algorithm. The DH algorithm basically gives you a systematic approach to assign coordinate frame, then assign the origins, getting the points BK and then getting all the DH parameters, joint parameters and link parameters and identify them from the manipulator configuration. So this is the first step in getting the forward kinematics. So once you have these parameters, then we can use it for identifying the transformation between these coordinate frames and get a relationship from this coordinate frame to this coordinate frame, that will become the forward kinematic relationship. So we'll stop here for 5 minutes. Oh, Tyagarajar College.
Yes, sir. I'm Muralidharan, studying ME Mechatronics from Tyagarajar College of Engineering, Madurai.
Okay.
Actually, I have a small doubts on assigning the coordinate frame for end effectors.
Okay.
It's not very sure for me. Can you explain one second?
Yeah, I can explain it, no problem. Okay. Yeah, so please look at the end effector like this. So in one of the previous classes, I don't know whether I explained it you. So assign the origin at the tooltip. That is the first thing. The origin will be LK, LN will be at the origin, and then Z will be like this. Z axis will be always the roll axis. Along the roll axis of the end effector, you assign the Z axis. Okay, so this is Z axis along the roll axis, and the Y axis is basically assigned along the open close direction of the gripper. Suppose you have a gripper, we assign that as the open close direction, that Y will be in this direction, and Z will be always assigned normal to this. So depending on the way you put Y in this direction or this direction, your X will be this direction or this direction depending on the right hand coordinate frame. So now if you look at this, so this is your Z axis, this is the Z axis and this is the Y axis. So this is the Y axis. So Z is in this direction, Y is in this direction. So X will be projecting out. So it will be like this, projecting out X N. So we call it as along the roll you have the Z axis, along the open close you have the pitch axis, and this one will be having the X will be the yaw axis. So yaw, pitch and roll will be the way you assign the coordinate frame for the last tip or the tool tip. Does that answer your question?
Thank you, sir. Thank you, sir.
Okay. So let us continue. So what we saw was to how to identify the coordinate frames and the kinematic parameters. The whole purpose of these parameters identification is to see how to represent the relationship between two successive coordinate frames in the manipulator. Yes, the whole objective is to map the tool coordinate frame. So you have a tool coordinate frame and you have a base coordinate frame. So this is the zeroth frame and this is the nth frame. So I need to map the coordinate frame or need to find a transformation matrix between these two coordinate frames. So in between we have many coordinates. So we have many joints. So there will be many coordinate frames. So using these coordinate frames I need to find the final transformation from here to here. So how much I have transformed from this coordinates, how much it has moved to reach this I need to find out. So to do that we need to develop a relationship between two coordinate frames and how the transformation between two coordinate frames can be represented using the DH parameters. So I have one coordinate frame here. So assume that I have a coordinate frame here x0, z0 and y0, and I actually move these coordinates and reach this position with a z like this, z1 and an x1 and a y1. So I just assume that this is the way I have a new coordinate frame here. So this transformation of this coordinate frame to this coordinate frame can be represented using DH parameters and using a matrix, and that matrix is known as the DH matrix or the transformation matrix, homogeneous transformation matrix, representing the transformation of two coordinate frames represented in terms of DH parameters. Or sometimes it is known as ARM matrix also, which actually identify a relationship between these two coordinate frames in terms of the DH parameters and see how this coordinate frame can be mapped to this coordinate frame. And we can always see that the transformation of this coordinate frame to this coordinate frame can be considered as a combination of four movements. We can actually see that this coordinate frame has moved from here to here some distance, and it has moved from here to here some distance. It has rotated by some angle with respect to x, and it has rotated by some angle with respect to z also. So basically the transformation of one coordinate frame to other coordinate frame can be considered as the combination of four individual transformations. That is, so you can see here, so this is the initial coordinate frame x0, y0, z0, and you have this coordinate frame x1, y1, z1, and that can be considered as it has moved from x0, y0, z0 to rotated at x0, y0, z0 first, and then moved and again moved by a and again rotated, and now it is in a position. So we can see that there are four fundamental operations, or we can identify four fundamental operations in transferring one coordinate frame to another coordinate frame, or this coordinate frame can be considered as a mapping from here to there through four fundamental operations. So we can say that a mapping, the four fundamental operations are involved in making k minus 1 frame coincident with kth frame. So if you want to make this k minus 1 frame to coincident with kth frame, you need to have four fundamental operations. That is, rotate Lk minus 1 by theta, Lk minus 1 by theta. You rotate this frame by theta, and then you rotate the rotated frame, you translate the rotated frame by a distance dk, and then again translate it by a distance ak, and then again rotate by an angle alpha k. So by these four operations we can completely define all the possible ways in which the coordinate frame can actually come to this position, or this can map with this one. And therefore the mapping between the kth frame and k minus 1 frame, the kth frame and k minus 1 frame can be considered as a combination of four fundamental operations: rotation by theta, translation by dk, translation by ak, and alpha, rotation by alpha. So this is rotated by with respect to zk minus 1. So this frame is rotated with respect to zk minus 1 by theta, and then it is translated dk with respect to zk minus 1, and then translated ak with respect to x axis xk and rotated by alpha k with respect to xk. So these 4 operations will make these two frames mapping, and therefore the coordinate transformation between this frame to this frame can be represented as a combination of r theta, that is a rotational matrix theta r, and then a rotation translation matrix dk, a translation matrix with respect to ak, translation of ak, and rotation of alpha k. So two homogeneous rotation matrices and two homogeneous translation matrices together will make the complete transformation from this coordinate frame to this coordinate frame, and therefore the mapping from the transformation matrix, the coordinate transformation matrix from k to k minus 1 can be mapped as a combination of these 4 matrices. So we can write this k to k minus 1, that is the mapping of kth frame to k minus 1 frame. So this frame to this frame can be considered as r, a rotation matrix r theta multiplied by a translation matrix d with respect to z, and then a translation a with respect to x, and a rotation alpha with respect to. So if you can do this, so this is actually the which actually represents the complete transformation of kth frame to k minus 1 or the mapping of kth frame to k minus 1 frame can be obtained by these 4 individual transformations: the rotation of theta angle, translation of d, translation of a, and rotation of alpha. The 4 dh parameters theta, d, a, and alpha brought into the transformation matrix, and then we define a coordinate transformation matrix which is known as the DH matrix or ARM matrix, which represents the mapping of k minus 1 frame to kth frame. That is what we are trying to do here. So k to k minus 1, the homogeneous transformation matrix from the source frame to the destination frame. So the mapping from k to k minus 1 source frame to the destination frame is the t k to k minus 1, which is a combination of or a multiplication of these 4 matrices R, T, T, R will give you the transformation matrix k to k minus 1, provided you know all the theta k, dk, ak, and alpha k. So if you know these parameters theta, d, a, and alpha, you will be able to map this frame to the base frame, provided what is the rotation, what is the translation, and what is the twist angle. If you know all this, you will be able to get this transformation matrix. So that is basically known as the ARM matrix or coordinate transformation matrix in terms of DH parameters. It's a homogeneous 4 by 4 matrix which maps the kth coordinate frame to the k minus 1 coordinate frame. Now we'll use this one. So once you do this, you'll be getting, so R theta we know that is a 4 by 4 matrix. It's a 4 by 4 matrix. So this is a 4 by 4 matrix. You know that is only translation means 0 will be the only rotation means this will be 0 and this will be 0, and depending on which with respect to which axis you are rotating, you will be getting a 3 by 3 matrix here. Similarly, when you have only translation, this will be non-zeros and all others this will be identity matrix, others will be 0. So by multiplying this, you will be getting a final matrix as shown here, which will be cos theta k. So this t k to k minus 1, k to k minus 1 is given by this matrix cos theta k first element, then minus cos alpha k sin theta k, and then sin alpha sin theta k, and ak cos theta k. And similarly, you will be getting this as ak sin theta k, and here it will be dk, and this will be 1, and you will be getting other elements also here as shown in the slide. You will be getting it as sin theta k, and then it will be cos alpha k, sin cos theta k, cos alpha k, cos theta k, then minus sin alpha k and cos theta k, and this will be sin alpha cos alpha yeah, sin alpha cos alpha alpha k dk. This will be 0, 0, 0, 0, 1. So this is known as the homogeneous transformation matrix in terms of DH parameters or DH matrix, DH transformation matrix or ARM matrix. This represents the mapping of kth frame to k minus 1th frame. So whenever you want to map a frame to one frame to the other frame, you can use this matrix, and if you know these parameters theta k, alpha k, ak and dk, you will be able to find out what is the transformation between these two coordinate frames that can be easily obtained. So that is basically the ARM matrix. So we will be using this ARM matrix to do successive transformation of coordinate frames to get the mapping from the tool frame to the base frame of the robot. So that is the way how we develop the forward kinematics. Okay, the inverse of this also is possible. So tk minus 1 to k also can be obtained by taking the inverse of this tk to k minus 1. So tk to k minus 1 inverse will be this one. So if you want to map from t0 to 1, you want to map, you will be able to use this matrix what is given. So actually its inverse can be obtained by taking the R transpose and then minus R transpose P principle, what I explained in the when we discussed about homogeneous transformation matrix. Okay, so how we use this for the forward kinematics we will see. So the direct problem is basically to map the tool frame to the base frame. So you have this tool frame. So this is the tool frame and you have all the joints here. So I put it as 0th joint, then there is 1, 2, 3, 4, 5 and this is 6, you can have n. So this is the nth frame and this is the 0th frame L0. So you have the x0, y0, z0 here, x0, z0 and you have this z6, zn, zn, yn and xn. So we need to have a mapping from here to here. So that is what our forward kinematics problem. So given the values of all these joint variables and joint parameters theta etc., how can I find out a mapping from this coordinate frame to this coordinate frame, because this coordinate frame represents the tool tip position and orientation. So when I change the parameters, how can I get this position and orientation is the forward kinematics problem. So it's basically from this is a Cartesian space. So from the joint space I need to map to the Cartesian space. So given the values of joint variables, solve for the end effector location and orientation or the position and orientation with respect to the robot base frame. So basically I want to have a mapping from this coordinate frame to this coordinate frame. So this is the position and this is the orientation. So I want to map this to this. Suppose it is n degree of freedom. So what I require is Tn to 0. So what is this transformation matrix? From nth frame to 0th frame is my forward kinematics problem. So the nth frame need to be mapped to the 0th frame, so that I will get the complete transformation of this frame to this frame. I will get the relationship, and this will be in terms of the joint parameters alpha, d and a. So this relationship will be as a function of theta, alpha, d and a, or theta will be the variable and all others will be constant. So if I know these parameters, constant parameters, if I know, I will be able to develop a relationship in terms of theta, what is the mapping from nth frame to 0th frame. And since we cannot get a direct relationship, what I will do, what we normally do is to, so this is the first one, so this is, I put it as okay 1, 2, 3 etc. the coordinate frames, okay, L0, L1, L2, L3 etc. So what I will do, I will take this one T1 to 0. So I will first find out what is the transformation from this frame to this frame. So I have another frame here and I have another frame here. There are coordinate frames assigned to each one. So I look at all the coordinate frames and try to map this one to here. So I first find out T1 to 0. What is the mapping from 1 to 0? I will find out using the DH matrix. If I know the parameters of A, D, H and alpha, I can get this 1 to 0 using the DH matrix what we discussed. And then I will find out T2 to 1. Then I will find out T3 to 2 and I will find out n to n minus 1. So each one I will find out separately. 1 to 0, what is the mapping from here to this? What is the mapping from this to this? What is the mapping from this to this? And this, each one I will find out. And then finally I write it as T n to 0 will be T1 to 0 multiplied by T2 to 1 multiplied by T3 to 2 etc. Tn to n minus 1. So this will be the relationship I will be developing. So I can get the transformation from nth frame to 0th frame by taking the individual transformations 1 to 0, 2 to 1, 3 to 2 etc. and n to n minus 1. If I can get all these individual transformation between successive coordinate frames and multiply them together and get the final transformation from n to 0, which will be the forward kinematic relationship for the manipulator. So the forward kinematics is basically a relation between this frame to this frame as a function of the joint variable. I will be able to get it this one as a 4 by 4 matrix, and these 3 elements at the will give the positions, and this 3 by 3 will give the orientation of the tool. So this will give the tool position, this will give the tool position px, py, pz, and this will give me the orientation 3 by 3 as normal, sliding and approach vectors. So I will get the complete position and orientation of the tool with respect to the base frame using this Tn to 0, which is basically the forward kinematic relationship. So n to 0 will be getting this n to n minus 1, 1 to 0 etc. And the last one, the n to 0 will be a function of this theta, and px, py, pz can be obtained from this element and orientation can be obtained from. So complete position and orientation. So this p is given by px, py, pz, and the orientation of this frame with respect to this base frame is given by this 3 by 3 matrix. So case of a tool to base, basically n is a tool and 0 is the base. The tool to base can be obtained as individually 1 to base, 2 to 1 etc. and then finally tool to the n minus 1 frame. So you can find out the individual transformation matrices and then complete get the matrix tool to base. You will get the relationship, forward kinematic relationship for the manipulator, and for any value of theta you will be able to calculate this px, py, pz because all this will be a function of theta 1 to theta n depending on the configuration of the manipulator. So that is basically the forward kinematic relationship. We will take one example and then try to solve it so that you will be clear about how to develop the forward relationship for a given manipulator. So this is a final tool to base that you will be getting as then we call it as arm equation because the complete individual matrices are known as arm matrix, and you have this Tn to tool to base, we will get it as a matrix that is known as arm equation because this will be a term with a lot of cos and sine and a, b etc. So you can write it as px is equal to something, py is equal to something in terms of as a function of theta parameter. So that's why sometimes this is known as arm equation also. So this is the PQ and this is the role. The 3 by 3 submatrix represent the tool orientation and the 3 by 1 submatrix represent the tool. So let us take an example to show how this can be developed for a given manipulator, the forward kinematic relationship. So we'll go take the same example that we discussed earlier where we assign the coordinate frame and try to find out the DH parameters. So I will not be explaining again how to do these DH parameters because we already saw that these are the DH parameters that you can get, and this is the way how the coordinate frames are assigned. As you can see in the slide, you can see how to get the how to assign the coordinate frames and then how to get the DH parameters. Now from these DH parameters, what we need to do is we have to get T5 to 0. So what we need to obtain is T5 to 0 is to be obtained, and that can actually be obtained by T1 to 0, T2 to 1, T3 to 2, T4 to 3 and T5 to 4. It's a 5 degree of freedom manipulator, and therefore 5 to 0 or the tool to base can be obtained by taking the individual transformations this way, and we have all these parameters. We have all these theta, a, d, alpha for all the 1, 2, 3, 4 and 5. So all these parameters are known, and therefore we can find out this T1 to 0 by simply using the DH matrix, which we already saw how to get the DH matrix 4 by 4, which will be cos theta k and cos alpha minus cos alpha sin theta etc. So we found that use this and get the individual transformation matrix and then multiply them to get the final transformation matrix. So if you look at, you can see this is the parameter and this is T120. So 120 is given as the DH matrix as in the slide. So you substitute the values of theta 1. So for T120, substitute the value of theta 1, A1, D1 and alpha 1. You will get T120 because the matrix is cos theta 1. This is cos theta 1 minus cos alpha 1 sin theta 1, etc. Substitute the value of this, you will be getting one matrix as T0, T120. So T120 you will be able to get. So it will be like this, cos theta 1. So cos 1, I will write it as cos 1, cos theta 1. Then 0 because your alpha is 90, alpha 1 is minus 90 and therefore this will become 0 and then you have minus sin theta 1 and AK is 0, here A is 0 and this will be the same way you will be getting this as sin theta 1 0, cos theta 1 0 because again A is 0, this is AK sin cos theta k, this is AK sin theta k, AK is 0, A1 is 0, so this both will be 0. And since DK, D1 has got a value, so this will be D1 here. So D1 has got a numerical value and this will be 0, minus 1, 0, 0, 0, 0, 1. So that is going to be the T10. The transformation of coordinate frame 1 to coordinate frame 0 will be this one, cos theta 1 sin theta 1 0 0 minus sin theta 1 cos theta 1 0 0 0 D1. So basically it tells that there is a rotation of alpha and a translation of D1. So that actually gives you this matrix T10. And then theta 1 will be the additional variable will be there. So depending on the value of theta 1, the T10 will be having different values. But D1 will be constant. So it's a constant value. There is no, it's not a function of any of these. So the T10 basically depending on theta 1, you will get a different orientation for the coordinate frame 1. So that is what actually it says. Now if you look at the coordinate frame here, you can see this initial L0, x0, y0, z0 and then x1, y1, z1. It is D1 away from the origin L0. So L1 is D1 distance away and it has rotated by 90 degree and that's why you get this matrix here. This is minus 1 and this rotation and then depending on theta 1 it will be having a different orientation. So as theta 1 changes it will actually move out of the plane or come inside the plane. So this actually change, the x-axis will keep changing because of that. That basically says T120. Same way you can get T20 and sorry T21 and T322. You will be able to get these two by substituting theta 2, A2, D2 and alpha 2 and get it. So it will be like this. So you can see the T120 then T220 and 320. If you multiply all these, basically you are actually, this basically represent the wrist position because that is the positioning axis. So this is basically the wrist position. This 3 transformation gives you the wrist position and from there the wrist you have a pitching and a roll. So wrist to base is given as T320. So in this case T wrist to base is equal to 320 is obtained as 120, 221 and 322. That is the wrist to base. That is what is shown here. So you multiply this, you will be getting a matrix and that will be a single matrix and that will look like this. So you can see the position elements of the wrist or the wrist position is given as the position of the wrist if you want to find out by so it will be P wrist x will be cos theta 1 A2 C2 plus A3 C3. That is the A3 C23. So C23 means theta 2 plus theta 3. Similarly, Py will be C1 sorry S1 S1 A2 C2 plus A3 C23. So that is going to be the wrist position Y. And the Pz also, wrist position Z also will be given as D1 minus A2 S2 minus A2 A3 S2 3. C23 means theta 2 plus theta 3. Cos of theta 2 plus theta 3 is given as cos theta cos C23. So that is for the wrist position. Now if you want to get the complete position, you can actually get it as T tool to wrist separately. Tool to wrist will be 4, 5 and 3, 4. So that will be tool to wrist. You take tool to wrist. So tool to wrist will be T4 to 3 and T5 to 4. That will be the T tool to wrist, and multiply this one with this one, you will get the complete tool to base can be obtained like this. So you will be getting this as tool to wrist, and the complete relationship from tool to base is given there in the slide. So that actually the last column shows the position vector of the tool with respect to base as a function of theta 1 to theta 5, or exactly in theta 4 in this case. You can see the position Px of the tool position Px is given as C1 etc. That is 177 is the A1 parameter, A2 and another A3 is there, and then D4 is there. So you can see A3 as a function of theta, the function of theta, A, D and alpha, you are getting a relationship for Px. Similarly, you get a Py, S1 multiplied by something and Pz also. So you are getting the position of the tool as a function of joint angles and the joint parameters, joint and link parameters, and that is actually known as the arm equation. So the complete tool to wrist relationship is known as arm equation, because the position of the tool with respect to the base given as a function of joint angle and joint variable. Now for any given joint angle theta 1 to theta 5, you will be able to find out what is the position it has reached, because that is the only variable in this case. Theta is the only variable. So if you know the joint angle for a given configuration, so if you know the joint angle, if the manipulator is like this, so if you know this joint angle, then this joint angle, you will be able to know what is the position by simply substituting the values of all these theta. So if you know theta 1 to theta 5, you will be, you substitute these values into this, you get the position and position achieved, reached by the tool and the orientation it achieved. This is the position, and the 3 by 3 matrix on the left side gives you the orientation of the tool with respect to the base frame. So that actually completely defines the kinematics of the manipulator with respect to the base frame in terms of the DH parameters. So this is a way how we develop the forward relationship for a given manipulator. Again, you can see that the Px, Py, Pz, it's not a function of theta 5. You can, if you look at the relationship, it says that Px is equal to cos theta 1 multiplied by 177.8 C2 plus 177.8 C2 plus 3 minus 129.5 sin theta 2 plus 3 plus 4. And the reason is that the position reached by this tool, whatever may be the roll angle, whatever may be the roll, the position is not going to change, and therefore the position is independent of theta 5. So whatever may be the angle theta 5, this position will remain the same because it's only a roll. Position is not going to change. That's why Px is not a function of theta 5, and that will be the case with most of the manipulator when you have a last roll angle, and the position will not be changing with respect to the roll axis, roll angle. Therefore, it will be independent of this one. So this is the way how we develop the forward relationship. Any questions on deriving the forward relationship? Please raise your hands, then we can, if you have any questions, I can clear them and then go to the, put one more example. I'll just take one more example and then show you how this is done, so that you will be very clear about developing the forward relationship. Because forward relationship is the most important one. Yes, for inverse relationship, you need to first develop a forward relationship and then solve for it to get the inverse relation. So forward kinematics, if you don't understand forward kinematics, you will find it difficult to follow inverse kinematics also. Okay, so let us take one more example, so that I'll make sure that all of you understand it clearly, and then you are capable of doing an assignment. So this is another example, another robot. It's a 6-axis robot. As you can see here, it is an IntelliDex 660T commercial robot. This has got 6 degrees of freedom, but it has got a slightly different configuration. You can see that there is a base joint, the base joint with a rotation like this, and then you have a roll axis is here, and then you have a pitch axis here, and then you have an elbow, and then tool pitch, then tool roll. So this is the pitch axis, and this is the elbow, this is the shoulder, and here also you have another axis also here. Okay, this is the rotation axis, and this is the rotational axis, and this is another rotational axis, tool pitch, and then roll axis is here. So you can see that the pitch axis is here and the yaw axis is actually missing, but if you rotate this by 90 degree, this pitch will become a yaw axis, because this axis, if I rotate here, it will become like this, then it becomes a axis like this. So that is what actually this joint helps us to get another rotation here by changing the direction of, by rotating this by 90 degree, you will be getting it as a pitch axis can actually convert into a yaw axis also. So that is the configuration of this manipulator. Say 6 degrees of freedom, just got all the 6 degrees of freedom necessary for manipulation, and we want to develop a relationship between, for this manipulator, this is a sixth one, so I want to get a relationship T6 to 0 for this manipulator. So I want you to work along with me. So first part is to doing the kinematics is basically to get the coordinate frames assigned, and once you assign the coordinate frame, identify the points BK and get the DH parameters. So the first part is assign coordinate frame, then to get the DH parameters. And if you make a mistake in assigning coordinate frame, your DH parameters will be wrong, and therefore your forward kinematics also may go wrong. But you can always cross check your forward kinematics by assuming a home position and finding out all the values of theta, and then finding out where the tool should be there. If this is the condition, you will be able to find out what is the Px, Py for this, and cross check your formulation. I will explain it how it is done. So let us start with the assignment of coordinate frame. So the first step is assign coordinate frame. So we will start with the base frame. As I explained, you start with your Z0, X0 and Y0 as usual, and keep going. And the only thing you need to make sure that is you always identify the origin of the coordinate frame, because here you will find that two cases the coordinate origin will not be at the same point. So look at the first one, Z0, then second one X1, that is this rotation is the next one, and then you have a shoulder roll, and therefore this shoulder roll frame also will be at the same point. You will be getting two frames at the same point. So this will be one frame. So L0 is here, L1 will be here, and L2 also will be the same point. So you will be having another rotation axis assigned here. As you can see in the slide, you will be having a Z axis here, Z2 will be here, this will be Z1. And then go ahead with the next one, Z3 axis. Again, you can actually decide to be a Z3 in this direction or this direction, it is left to you. And go for the next one, Z4 axis, and then the Z5, the roll axis, again the origin will be same point. This will be having two, this will be L5 will be here and L4 will be here. L4 and L5 will be at the same point. If you apply the rule of identifying the origin of the coordinate frame, you will be able to find this. So this will be the origin L5. Now once you have this, you try to find out the, okay, now last one is this one, L6 will be the coordinate frame. So you have the Z6 here, and then open close and y axis and x axis assigned here, the tool tip. So that becomes the last coordinate frame, L6, origin is L6. So now we have L0 to L6 assigned. Now look at the BK, identify the position BK, B1, B2, B3, B4, B5, etc. So B1 will be here, and again B2, B3 will be here because of the origin coinciding. We will be getting B1, B2, B3, and then you will be able to find out the DH parameters. So if you go with the procedure, you will be getting the DH parameters as shown in the slide. So you will be having a D1. So this will be the D1 distance, and then this is D1, and this will be the D6. You will be having a D6 here. Between these will be the D6, and A1 will be 0, A1, A2 will be 0, you will be getting A3, this will be A3 and this will be A4. So A3 and A4 will be there. So this is D1, D6, A3, A4. So D2, D3, D4, D5 will be 0, A1, A2 will be 0, A5, A6 will be 0. If you follow the rules of identifying the DH parameters, you will be able to see that these are all actually, others will be 0. And similarly, the alpha, that is the twist angle, you can see the Z0 to Z1 there is a rotation, Z1 to Z2 there is a rotation. So you will see that there will be a 90 minus 90, then 90, that kind of rotation axis will be, I mean alpha will be there, then again 0, then 90, 0. So that will be the twist angle alpha, alpha k. So alpha k will be 90 minus 90, 90, 0, 90, 0. You will be able to see this when you look at the coordinate frames and then follow the rules of getting the parameters. You will be able to identify all these parameters. Then AK, as I told you, and theta, all the thetas are variables. So theta 1 to theta 6 are variable. So we'll put it as theta, all the thetas variable, and then get the other parameters, all the other DH parameters. So once you get the DH parameters, next one is to get the arm matrix. So you find out all the arm matrices, T1 to 0, then T2 to 1, T3 to 2, T4 to 3, T5 to 4, and T6 to 5. So you get all these, and you will be able to get T6 to 0 or T2 to base by multiplying these, all these together. You will be able to get the tool to base. So 1 to 0 will be a function of D1, A1, theta 1 and alpha 1. That will be a 4 by 4 matrix. So each one will be a 4 by 4 matrix. So this will be a function of only theta 1, this will be a function of theta 2, this will be a function of theta 3, theta 4, theta 5, theta 6. Okay, so this is, oh sorry, this is theta 1, theta 2, theta 3, theta 4, theta 5 and theta 6. So 6 variables, and you will be getting, so finally when you multiply this, you will be getting Px, this Px, Py, Pz as a function of these joint variables, and it will be a long expression because you have 6 matrices. When you multiply all these 6 matrices, you will be getting a long expression for Px, Py and Pz as a function of these joint variables. And when you, if you write a computer program, you can substitute all these values and then substitute, give it that as a output. So you'll be able to get it as a 4 by 4 matrix without much of a difficulty. That's why writing a code for forward kinematics will be much more easier than doing it in analytical. Okay, so how do you cross check this position is that this position, what I have shown this position, if you measure the theta or you calculate theta, you will see that theta 1 is equal to 90. Okay, because normally we assume theta is 0, but assume that this is the home position, and for this position x0 to x1, x2, x2, etc. So x0 to x1, x2 can be calculated, x1 to x2. So you will be getting theta 1 is minus 90 minus 90, 90, 0, 90. Okay, 1, 2, 1, 2, 3, 4, 5. One more is 0. So this will be the theta 1 to theta 6. Because it's easy, all theta 1 90 0. So you can actually substitute this in the final equation and then check. When you substitute these values, you should get Px is equal to this plus this plus this, because A3 plus A4 plus D6 should be Px, because this is the x direction base coordinate from x0 and this is the tool position. So under this position, the Px should be equal to A3 plus A4 plus D6. If you are able to get A3 plus A4 plus D6 as the value for Px, when substitute this theta into this relationship, that means your forward kinematics is correct. You have not done any mistake in calculating. If you are not getting this, then something is wrong with your calculation, either in the calculation of theta or in the calculation of the forward relationship. Similarly, PZ, this is the Z axis of the base frame. So PZ should be equal to D1. So PZ should be always equal to, D1 under this condition. If the theta is equal to this, then D1 should be, PZ should be D1 and Py should be 0 because it is in the same plane, XZ plane, does not rotated, and therefore Py should be always 0. So under this condition you will be able to get, you can be able to say that your forward kinematics is correct. So I'll just briefly tell you, okay, this relationship. So the matrix will be elbow to base and then base to, this will be the elbow to base in this case because we put this elbow is here. So elbow to base you can get the first relationship, and then Pvx will be cos 1 cos C1 C2 C3 plus S1 S3 multiplied by A3. Py will be S1 C2 C3 minus C1 S3 A3. So similarly you can get the base relationship also. Okay, if you want to check this as a partial cross checking, you can actually find out up to this position what is the position here. So this is the elbow and you want to check that your elbow part is correct. Your Px should be equal to A3 and Py should be equal to D1. That is a cross check. So you will see that you will be able to get it. So this is A3, 0 and D1. So if you substitute for the elbow to base, so if you calculate elbow to base and substitute the values of theta, you will get that Px is equal to, here you will get A3, 0 and D1, and all others will be 0, this matrix will be there. That means the Px, this position is A3, so your Px will be A3 and Pz will be D1 for elbow. And that is a partial cross checking of the forward kinematics. And if you do the full relationship, tool to elbow and then get the tool to base, the relationship will be like this. So what actually I have shown is only the position vector Px, Py and Pz because it's a long relationship, a long matrix, big matrix. So we are actually seeing Px is equal to C1, C2, A3, C3 plus A4, C3, 4 plus D6, S3, 4, 5 plus S1, A3, S3 plus A4, S3, 4 minus D6, 3, 4, 5. That is the Px, then similarly Py and Pz. And the rotation part will be this one. This is a 3 by 3 rotation part will be like this. So approach vector, sliding, normal sliding and approach vector you can see. The normal is the first vector, sliding and approach vector. And you can see approach vector is independent of roll angle, and similarly the position PQ is also independent of theta 6. You can see Px, Py, Pz, they are independent of theta 6. It's not a function of theta 6. Similarly, the roll is also the approach vector R3 is independent of roll angle. So whatever may be the roll angle, it will always pointing in one direction. That vector will remain same, whatever may be the roll of the tool. That's why this vector will remain same. It's independent of theta 6. Now as a partial check, if you substitute in this PQ relationship Px, Py, Pz, you substitute the value of theta 1, theta 2, theta 3, theta 4, theta 5 and theta 6 into this relationship, you will get Px, Py, Pz. And if you see that, you will see that this is the way how you will get it. So tool to base, the tool to base relationship, you will see that Px is equal to A3 plus A4 plus D6, Py is equal to 0 and Pz is equal to D1. That basically says that we are done properly for this position of the robot. Px is A3 plus A4 plus D6 and Pz is D1 and Py is equal to 0. So by substituting these values into your forward relationship, you are able to see this one. So that actually completes the forward relationship for the manipulator. Okay, this is a homework for you. A Rhino XR3 robot. Develop the forward kinematic relationship for the robot here. It's again 1, 2, 3, 4, 5, 6 degrees of freedom robots. It has got a roll axis, pitch, yaw, and then shoulder, elbow and shoulder also. So you can use the same principle whatever we discussed. You can identify a home position and then try to develop the forward kinematics for this manipulator. In case you have any difficulty, you can always contact me, or in the next class you can ask me the question, then we will be able to clear your doubts. Okay, apart from this, I have an assignment for you. Okay, so before closing, let me have few pop-up questions just to know whether you are, just to make sure that you understood something. Forward kinematics problem is to map the joint space to Cartesian space, identify the joint parameters and link parameters, map Cartesian space to joint space. Answer A, B or C. What is the purpose of forward kinematics problem? What are we trying to map here? A, B or C? We are mapping actually the Cartesian joint space to Cartesian space. We know theta, we have to map to Cartesian. Answer is A, joint space to Cartesian space. Joint parameters and link parameters is not exactly the forward kinematics. Of course, we need to know that. The answer is actually A, we map the joint space theta to x Cartesian space. The second one, in assigning coordinate frames, joint axis is always assigned as x, y or z axis. Okay, C. I can see many C's here. That's right. Assigning coordinate frames, joint axis always assigned as z axis. Okay, next one. The origin of a joint coordinate frame will always be at the physical location of the robot joint. This statement is true, false, or depends on the type of joint R or P, it will be true or false. The origin of a joint coordinate frame will always be at the physical location of the robot joint. Is it true, false, or it depends? Okay, there are B's and C's. Okay, B is correct. It's a false statement because it need not be at the physical location of the joint. It can be, it actually depends on the way we assign the coordinate frame, and then we look at the intersection of the joint axis for the k and k minus 1. Okay, the last one. In the right-handed coordinate frame convention, the thumb represents, simple question. Right-handed coordinate frame, the thumb represents x, y or z. I can see B, C, A. Okay, I can see more A's now. The correct answer is A. It actually represents the x-axis. So thumb is x-axis, pointing finger is y-axis, and middle finger is the z-axis. Okay, that's all about the pop-up questions. I have an okay, we'll discuss about the inverse kinematics in the next class. Time is over. I have an assignment. I think that will be uploaded by the QEEE team. So you can look at the assignment and try to solve it. I have one problem for assigning coordinate frames and getting the forward relationship, and another problem is to write a code either in C or MATLAB to do the forward kinematics of a n degree of freedom manipulator. Okay, thank you very much. We'll discuss about the inverse kinematics and the velocity relationship in the next class. Thank you very much. In case you have any questions, please feel free to send me an email, or you can contact the QEEE team. We will be able to, I'll be able to help you with your doubts. Thank you very much. Have a nice day.